Let's take a look at two instances of hypothesis testing. I've selected two exercises directly from the book, and I'm fleshing them out as examples for you to follow along. The first one is from the quiz at the end of Chapter 7, and it's problem number 3. You can read it directly from the book if you want more detail, but it's basically a claim that we have salaries of $47,254. And that's the direct claim. When there's a direct claim like that, it's pretty automatically the null hypothesis because of the equality. So we can say the null hypothesis is that the sample mean is going to turn out to be 47,254. The alternative is simply that that's not true. It's not equal to 47,254. This makes it a two-tailed test because we're told that we're going to use the 5% level of significance. That basically tells us right away that we are looking at 0.025 on one side and 0.025 on the other side in a two-tailed test. Let's check out what sort of information we have. We're told that the sample is only 15 elements. Well, that's a fairly small number, and we aren't given any useful supporting information. We're going to have to go with the t-distribution. And in particular, the degrees of freedom for this t-distribution are going to be 14. We weren't told that we could use the normal distribution, and the sample size isn't big enough to justify that. So let's take a look at what we're going to need to find for our critical numbers. All right? So we have 14 degrees of freedom, and we want 0.025. When we look at the table for 14 degrees of freedom, we find 2.145. That's in table 5 of the t-distribution, looking at two tails with 0.05. So let's write that down. It's going to be minus 2.145 on one side and positive 2.145 on the other side. Those are the rejection tails. If we fall into those regions with our statistic, we have to reject the null hypothesis. What sort of data are we told we have? Well, we're told the following. We're told that our sample mean came out to be $50,781, which is on the high side. Is it high enough to form rejection? Let's find out. We need more information. We were not told that we had a normal distribution. We were told that we don't have sigma. We have to use S, and we were told that S is 5,290. We have all of our pieces now, because remember, when we take our critical number and compare it with our statistic is a t-statistic, and it goes the same way as many of our calculations. You take x bar, you subtract the supposed mean, you divide by, well, it's not standard deviation, it's sample standard deviation, S instead of sigma, but we still have to divide by the square root of n. When we put all of this together, we have 50,781 minus 47,254, all divided by 5,290, all divided by the square root of 15. Grab your calculator, do a little bit of crunching, and you find out that you have 2.58, and there's more, 2, but 2.58. So T is 2.58. Where is that on our T distribution? Well, it's way over here. It's well into the rejection region. So we say reject the null hypothesis, reject the assumption that the mean is 47,254, and it appears in this case it's something else. It's the alternative hypothesis that we will accept. So that's one example. Now let's take a look at a different problem. This is from the review exercises, and I'm borrowing the numbers from problem 59. In this case, if you look at problem 59, we are told that a bolt manufacturer is making a claim about the variance of the bolt widths. The claim is that the variance is at most 0.01. The variance, sigma squared, is at most, well, that's less than or equal to 0.01. Now, you and I know that the null hypothesis has to be the one that has an equality in it. So, once again, this claim is the null hypothesis, and the alternate hypothesis is always the complement. What's the opposite of less than or equal to 0.01? It's greater than 0.01. And we have to find out which of these hypotheses we will accept. We'll be rejecting one and accepting the other. The level of significance for this problem, we are told, is, brace yourselves, 0.005. Okay? So that's not 1/2 of 1%. That's 1/2 of 0.00. Okay? So it's 1/2 of 100th. What are we going to do with that? Well, this is a chi-square problem because we're checking variance. We are told that we have a sample set of size 28, so we're going to be looking at 27 degrees of freedom. Chi-square curves are a little bit interesting. They're not at all symmetric. They go up and then taper off, and we want 0.005 for 27 degrees of freedom. If we go hunting in our tables to see where that comes up, it's table 6 for chi-square, and you will notice that if we are checking for 27 degrees of freedom and 0.005, okay, for the right end tail, let me move that down. Okay, that's what we want. Down here we've got 49.645. So let's write that one down. 49.645. And our rejection region is right there. So we need a fairly large statistic to fall into that region. Let's see the sort of information we're given. We are told that when we sample, there's no X bar in this case. We're looking at the sample variance. And the sample variance, we are told for this sample of 28, is 0.064. And we already know our critical value right here for our chi-square statistic. Let's find out what we're going to get when we do our computation and compare it to that critical value. The formula is pretty simple. We take n minus 1, the degrees of freedom, we multiply by s squared, and we divide by sigma squared, where sigma squared, of course, is going to come from our hypothesis. In this instance, we're going to get 27 times 0.064. We divide by 0.005. 0.01, and our computation comes out to be a whopping 172.8. Well, our critical chi-square value is just up here around 50, and we have something above 172. So right here is where we have our breakpoint, and our chi-square result, our statistic, is way off the side. So what do? We have to reject the null hypothesis. Again, there's not enough in our statistic to support that, and so it appears likely that the variance exceeds the stated amount of 0.01. And now we have two more examples of hypothesis testing to consider.